In this lab, we are examining the arc-shaped motion of a spring mass system acting in 2 dimensions and comparing it to a computer model in VPython. Like the previous labs, we are able to use fundamental principles like Newton's second law and the energy principle to predict the motion of this system. We are also looking at whether or not our model satisfies the energy principle. I found that my model matched my data pretty well, and that my model satisfied the energy principle, but I will discuss this in more detail later. Here's the tracker video I used in my lab, which shows the oscillation of the spring mass system in 2 dimensions. I set my origin at the point of attachment of the spring, and I calibrated the length with the stretch length of the spring, which is 0.7 meters. Like all of the other labs, I used Newton's second law to help me predict the motion of the system. Here I have 2 forces acting on my system, the force of gravity and the force of the spring. I use Newton's second law to update the velocity and position inside my loop. I am also using the energy principle in my model. This states that the total change in energy is equal to the change in kinetic energy plus the change in spring potential energy and the change in gravitational potential energy. Here are the equations for each of these energies. Because no work is being done on my system, I know that there should be no change in energy within my system, so this equation should all be equal to 0. I had to do some calculations based on my tracker data to get some of the conditions for my model. I found the period by looking at my data and finding how long it took to make one oscillation. I then manipulated this equation here to solve for the spring constant. I then found L naught by setting the magnitudes of the spring and gravitational forces equal to each other, and then setting the equation so that I was solving for L naught, or the relaxed length of the spring. Here you can see where I input my initial conditions into the model.
This included the ball's mass, which was given, the ball's initial position, which was found from my tracker data, and the ball's initial velocity, which was 0 because it started from rest.
Here, I then told my code to read the data from a CSV file that I had created from my tracker data. I then input my values for the spring constant and the relaxed length, which I just calculated in the last slide. Next, I wrote code for the kinetic, gravitational potential, and spring potential energies of my system. I set my while loop equal to 9.307 seconds, which is how long my tracker data was recorded.
I then wrote code for Newton's second law here to update both the position and the velocity of the ball within my loop,
as well as the change in length of the spring. Then I set up equations to compute the change in energies in my system. Now I will run the code. The red ball represents the motion of our data, and the spring and the blue ball show our model. The blue arrow pointing up represents the spring force, while the black arrow pointing down represents the force of gravity. As you can see, the magnitude of the spring force changes, while the magnitude of the gravitational force stays the same. The graph shows the y position of the data versus the y position of our model, in the respective colors of the balls. The slight difference in their motion could be due to a drag force in the data which we didn't account for in our model, which would explain why the difference in their motion became greater over time. The difference could also be due to some error when I identified the points in my tracker data. Now I am running the program again to create a graph showing the energies of my system. The blue line represents the change in kinetic energy, the green line represents the change in gravitational potential energy, the red line represents spring potential energy, and the yellow line represents the change in total energy of the system. As you can see from the graph, as the spring potential energy increases, the gravitational potential energy decreases, and vice versa, which makes the change in potential energy equal to 0. Because the kinetic energy has twice the period of the potential, it has no change in energy over the same amount of time. As the yellow line along the axis shows, there is no change in total energy, meaning that this model satisfies the energy principle shown here. As these two graphs from Tracker show, the periods from the oscillations in the y direction or the x direction are slightly different. This is due to the fact that they depend on different properties of the system. The oscillations in the y direction depend on mass and spring constant, which is what I used in the lab, and the oscillations in the x direction depend on the length and gravity. In conclusion, the energy principle was satisfied by my model. We found that using either the x or y position to calculate the period will give you a slightly different value for t. Most importantly, we learned that we can still use fundamental principles to predict a more complicated motion.